Our world is becoming more and more complex and mysterious. Some pessimists argue that scientific progress and society itself will soon come to a standstill due to information overload. I don't think this is a serious cause for concern. As science moves forward, more and more systems and patterns are being discovered in nature. Scientific achievements lead to the fact that the facts that seem to us disconnected are becoming less and less. There is no need to register the fall of each apple, because thanks to Isaac Newton, we understand how gravity attracts everything to the Earth, from apples to spaceships. We can understand and calculate the behavior of the simplest building particles of our world, atoms. The laws and forces governing them are universal. Atoms behave the same everywhere, both on Earth and on the most distant stars. We have studied these basic phenomena deeply enough so that engineers can develop mechanical creations of the modern world, from radios to rockets. Our understanding of the Earth has been changing under the influence of great generalizing ideas. So the theory of continental drift helps us to combine a number of geological and ecological models on the whole planet. Charles Darwin's greatest insight, evolution through natural selection, reveals the underlying unity of the entire system of life on the planet. Whatever individual human lives may be, our environment is neither chaotic nor anarchic. There are models in nature. Models permeate everything, from human behavior, the growth of cities, the spread of epidemics to the development of technologies such as computer chips. These laws and models are the great achievements of science. In order to detect them, talent was required, and in some cases, genius. But to grasp their essence is not so difficult. We are all capable of appreciating music, even if we don't know how to compose or play it. Scientific ideas can also be understood and appreciated by everyone. Now science is invading our lives more than ever. Many political issues, energy, health, the environment, have a scientific background. The way science is applied concerns each of us. Important decisions should not be made only by scientists, but should be the result of broad public debate. But in order for this to happen, we all need to learn to feel the key scientific ideas. In addition to their practical benefits, they should become part of our public culture. Unification theory, one example of which is string theory, explains how everything in the universe is interconnected. Great scientists have spent years trying to develop a theory of everything. Unlike homegrown theories that we all like to come up with, scientific theories are supported by accurate data obtained as a result of carefully planned and controlled experiments. Theory in science is a logical creation. It reflects the most accurate experimental observations and a deep understanding of how the world works. However, a scientific theory is not at all obliged to embody the absolute truth. So far, it only reflects the state of our knowledge. There is always a chance that a new fragment of the obvious will come out, refuting the theory and sending theorists back to the starting point. One example of this is our vision of the solar system. In the 2nd century AD, the Greek philosopher Ptolemy developed a theory according to which the Earth is located at the center of the solar system. This was a logical explanation for the primitive astronomical observations of that time. But at the beginning of the 17th century, the Italian astronomer Galileo Galilei began to monitor the heavens with a newly invented telescope, thanks to which observations of the solar system became much more accurate than observations with the naked eye. In his observations, Galileo Galilei discovered details that coincided with the new theory of the Polish astronomer Nicholas Copernicus, put forward 100 years before. The Copernican theory reflected the picture known to us: the Sun, not the Earth, is at the center of the solar system. Since then, many observations, including space research data, have confirmed the heliocentric model of the solar system. Other failed theories include the flat Earth theory, phlogiston theory, an early attempt to explain the origin of fire, and the so-called intelligent design theory. Our theoretical understanding of almost all branches of modern science has developed due to the fact that old, obsolete theories have been replaced by new and improved ones. The theories that make up the backbone of scientific knowledge today permeate all areas, from the origin of the universe to the structure of the human mind. The principle of least action. The essence of this theory is that actions are performed in a way that requires the least effort. So the light beam will move in a straight line, since this is the shortest path between 2 points. If you throw the ball, it will go to the center of the earth. It is not known exactly who put forward the principle of least action, but if you think about it a little, then your everyday experience will most likely also prompt you to this idea. However, in the 18th century, this issue was the subject of controversy. Some of the greatest scientists in mathematics, such as Leonhard Euler, Pierre de Fermat, Gottfried Leibniz and Voltaire argued about who first put forward this idea. At that time it was important to give birth to such ideas, because they led to the creation of equations describing the motion of bodies under the influence of forces. They also led to the concepts of potential and kinetic energy. The principle of least action, unlike other theories, the principle of least action is just common sense. Movement in nature always chooses the simplest and shortest path. When Isaac Newton sat down and thought about how objects move, he developed 3 laws that have become so familiar to us that they seem self-evident. Firstly, he stated that the body has inertia, that is, it can resist changing the speed of its movement. Inertia means that the body remains stationary until you give it a push. Similarly, moving objects continue to move unless something stops them or gives them acceleration. Secondly, body weight determines what effect a certain effect will have on the movement of the body or lack of it. The third law, the most famous, states that every action has an equivalent and opposite reaction. If I push you, I will feel the same push in response. Space rockets and jet engines work according to this principle. When exhaust gas is ejected from the nozzle in the pipe, the engines receive a push forward. That's why you should be careful when getting out of the boat. Moving forward, you will certainly push the boat back. If you do not take this into account, you risk being in the water. The laws of motion are all that is needed to describe how bodies move in everyday life. Newton's ideas made it possible to make a trip to the moon in the future. It took 300 years just to invent the rocket necessary for this. The law of universal gravitation, this description of one of the fundamental forces in nature belongs to the greatest achievements of science. Isaac Newton formulated this law in 1687 as a fragment of his brilliant Principles of Mathematics, a 3-volume description of the science of mathematics. The law of universal gravitation states that everything that has mass, that is, everything that consists of ordinary matter, has a mutual attraction. This attraction depends on the mass of the 2 objects, the distance between them and a constant known as the gravitational constant. One of the main ideas of this theory was that the force of gravity adheres to the law of inverse squares. This means that the attraction between 2 bodies decreases with a value equal to the square of the distance between them. Newton's formulation of this law was so precise that it immediately explained the motion of the planets. Also, thanks to him, it became possible to launch rockets into space. After Einstein put forward the theory of relativity and with its help explained some anomalies in the orbits of the planets, it became clear that Newton's law is not the last word in the matter of gravity. However, it is almost universally accurate if applied by the gravitational pull that we encounter in everyday life. Big or small, everything falls to the ground with the same probability. What would you see if you were sitting on a beam of light? Albert Einstein asked himself this question when he was still a boy. The answer he found, the theory of relativity, destroyed the ordered universe described by Sir Isaac Newton 250 years earlier. Almost 100 years after Einstein, today's physicists are still trying to figure out exactly what his theory meant. Albert Einstein was born in the south of Germany in 1879 year. His father Hermann was an unsuccessful entrepreneur. When the family's well-being deteriorated to the limit in the 1890s, Albert was left alone in Germany to receive an education, and his parents went to work in Italy. At this time, Albert had already begun to conduct his own scientific research and dropped out of high school at the age of 16. Despite the lack of school education, he received a place at the Technical College of Zurich in 1896. Einstein continued to study a lot at home, and his college attendance left much to be desired. After his graduation, Einstein's bad reputation prevented him from continuing his teaching career. He joined the patent office in Bern and in 1903 married Milevy Marek. Uncomplicated work left him a lot of free time to think about physics. The year of miracles in Einstein's life was the year 1905. He has published 4 articles. One of them, about the connection between light and electricity, won him the Nobel Prize. The other became the starting point for the theory of relativity. 10 years later, Einstein published the general theory of relativity. This theory combined his ideas about energy, mass, and gravity into a single concept called spacetime. His life was shaken by the World War and personal problems, but Einstein continued to work. His main goal was to combine relativity with theories about atoms, creating a single unified theory of everything. This work remained unfinished after Einstein's death in 1955 and remains unfinished to this day. Enter the sea, expose your body to the waves and you will feel how much energy is contained in them. Surprisingly, they carry energy in completely different ways. Some waves, such as sea and sound waves, physically move particles of water or air or some other medium through which they pass. There are 2 types of these waves. A sound wave is longitudinal if it creates vibrations that move the air parallel to the direction of movement of the wave. Transverse waves, for example, electromagnetic waves, oscillate in a direction perpendicular to the direction of their motion. Polaroid sunglasses are effective because they block transverse vibrations moving in a certain direction, for example, up and down. Any light waves oscillating in a different direction, for example, from side to side, pass through unchanged. If the light were a longitudinal wave, the Polaroid lenses would be absolutely useless. Most of the wave theory was developed in the 19th century, when pioneers such as Thomas Young showed how waves could be affected. Waves are reflected by certain materials, refracted when they pass through the boundary between 2 media, or scattered when passing through a narrow hole. There are waves everywhere, in the ocean, in the air and even in the vacuum of space. Wherever they are, all waves have a wavelength, the distance from the beginning of one phase to the beginning of another. If a wave moves at a speed of 1 wavelength per second, then it has a frequency of 1 Hz. A wave in the ocean can have a frequency of 0.2 Hz, and a light wave has a frequency of about 500 trillion Hz. If you want to understand how heat moves, you should master thermodynamics. This theory is governed by 3 laws. The first one says that no matter what happens, all the energy in the universe remains unchanged. In other words, you cannot create or destroy energy. You can only transform one form of energy into another. The second law states that the entropy of a closed system is constantly increasing. Entropy is a part of the internal energy of a closed system that cannot be used in any way. So, as the clock spring unwinds, there is less and less force left in it to keep the clock going. Its entropy increases as the potential energy of the spring is slowly transferred to the arrows as kinetic energy, and part of the energy is lost as heat due to friction in the mechanism. The third law states that as the temperature in the system tends to absolute zero, the lowest possible temperature minus 273.15 of a degree Celsius, all natural processes cease and entropy reaches a minimum. As a result, it is impossible to reach absolute zero, because no processes can lead you there. According to the theory of thermodynamics, the refrigerator does not add cold to your products, but takes their heat away from them. He does this by compressing the liquid in the tubes on the back of the device. The aerosol gets cold when you use it. The refrigerator works the same way. The expanding liquid turns into a cooling gas, and then the compressor turns the gas back into a warm liquid. Electromagnetism is an incredibly powerful idea. Without him, our life would not be known. This is what happens when you combine electric charges, motion, and magnetic fields. Move the metal wire within the magnetic field, and an electric charge will rush into this wire. This is how we produce electricity. On the contrary, direct an electric current through a wire and the movement of electric charges will create a magnetic field. This is how we create the electromagnets that drive most doorbells and charged particle accelerators. The third option is to pass an electric current through a wire located in a magnetic field. The wire will start moving. This idea made it possible to create an electric motor in your kitchen blender and electric drill. The creation of the theory belongs to the Scotsman James Clerk Maxwell, who was the first to write down an equation describing the complex interaction of electric and magnetic fields. It turned out that the equation required an unexpected component, the speed of light. This discovery led to the understanding that light and radiant energy can be represented as moving vibrations in electromagnetic fields. These moving fields became known as radiation. Amazingly, the flow of invisible particles and the influence of an invisible force field can fill everything with energy, from a toy car to a super-powerful computer. An electromagnet is a magnet that has received energy from an electric current, so that it can be turned on and off. Such magnets are used in electric motors. Einstein's theory of relativity is the most accurate description of how matter, energy, space and time interact. There are actually two theories: special relativity and general relativity. The special theory of relativity appeared first. It said that nothing could move faster than the speed of light. She also showed that the passage of time is different for people traveling at different speeds. According to this theory, if you separate the twins and send one on a journey into space at a speed close to the speed of light, then when they meet again, their ages will vary significantly. The special theory of relativity also gave rise to the famous equation E equals mc squared, which describes how matter can be converted into energy and vice versa. Based on this equation, the atomic bomb and nuclear energy were created. A later theory, the general theory of relativity, changed the understanding of gravity proposed by Isaac Newton. It describes time as a dimension, the same as the three dimensions of space, and combines them all into something called spacetime. Everything is relative. We often say these words, but we don't fully understand how true this is. Even time, mass and space are interconnected. According to the theory of relativity, the faster you move through space, the slower you move through time. If you reach the speed of light, time will stop completely. Atomism was originally proposed in the 5th century BC by the Greek philosopher Democritus, who believed that everything in the world basically consists of combinations of small, solid and invisible particles. He called these particles atoms and suggested that they come in different shapes and sizes, but all consist of the same basic material. The modern scientific theory of matter asserts that the vast variety of substances that we observe in the universe consists of combinations of various chemical elements. These elements really consist of trillions of identical particles, or atoms. The internal structure of an atom is characteristic of each element. Thus, the hydrogen atom has a different structure than the gold atom. The modern theory of atomism began in the early 19th century with the work of the English chemist John Dalton. However, it was not until 1905 that Einstein mathematically proved the existence of atoms. A few years later, Ernest Rutherford became the first to look inside atoms as part of an experiment in which he bombarded a thin gold sheet with alpha particles. He discovered that each atom consists of a tiny, positively charged nucleus surrounded by an empty space in which even tinier negatively charged electrons revolve around the nucleus. Everything you have ever seen, can see, and will see in the future, consists of a bunch of atoms. Even you yourself. This is an incomprehensible, but incredibly powerful theory of the subatomic world, in which everyday concepts concerning forces and motion are no longer applied in the usual way. Instead, we need a new kind of mechanics based on quantum rules. This idea was first developed in the early 20th century by the German physicist Max Planck, who suggested that energy comes in tiny fragments called a quantum. In the 1920s, Albert Einstein, Niels Bohr, Paul Dirac and Werner Heisenberg continued to work on this theory. However, despite the huge success, quantum mechanics remains under the veil of secrecy, because unlike other scientific theories, no one knows exactly how and why it works. She makes some predictions about the microscopic world, and they completely contradict our common sense. For example, it explains how an atom can exist in more than one place at the same time until we check exactly where it is. She also claims that an electron can simultaneously rotate both clockwise and counterclockwise. Until we measure it. Quantum mechanics asserts that the same subatomic particle can simultaneously exist in a number of different states. Heisenberg's uncertainty principle. It is a theory about how quantum objects such as atoms and smaller particles inside atoms behave. The principle was developed in 1927 by Werner Heisenberg and named in his honor. According to this principle, we never know exactly where the electron is located. Although at the same time we know exactly how fast it is moving, both qualities, their speed or position, can in fact be measured infinitely accurately if the value of another quality is sacrificed. And it's not because of our lack of understanding of how nature works, and not because of the smallest size of an electron, but because electrons are just like that. In fact, it has nothing to do with us. The electron itself does not have a precisely defined position and velocity. The best we can do is to determine the region in which a given electron is most likely to move. The uncertainty principle also affects concepts such as energy and time. We can measure the exact energy of a particle, unless we wonder at what point in time it has this energy. Conversely, if we accurately determine the measurement time, we will have to give up all hope of finding out how much energy it has. According to the uncertainty principle, by measuring subatomic particles, you can only get a limited amount of information. In the mid-1930s, the Austrian physicist Erwin Schrödinger proposed a thought experiment to show how crazy quantum mechanics is. He offered to take a box and put a cat in it, some deadly poison and a source of radioactive radiation. According to quantum mechanics, we cannot tell until we check whether a radioactive atom has decayed within a given time. So we have to describe it both as a decayed atom and as not decayed. Only after verification will we force it to be either one or the other. Inside the Schrödinger box, the experiment is designed so that any decayed atom would release a particle that triggers the release of poison and kills the cat. Since the cat, according to Schrödinger, also consists of atoms, albeit trillions of atoms, it is also supposedly subject to the laws of quantum mechanics. So until we open the box and look inside, we have to describe the cat as both dead and alive at the same time. Only when we open the box will we identify everything inside it as being in one of these states. Schrödinger used his thought experiment code in a box in a dispute with Albert Einstein. But it also helps us describe the workings of quantum physics. Richard Feynman and his many collaborators have reshaped our understanding of quantum physics. This is a world of incredibly small particles that make up the fabric of the universe. Like all brilliant scientists, Feynman was an independent, free thinker. He is known not only for his insights, for which he was awarded the Nobel Prize, but also for his groovy bongo playing. Richard Feynman was born in New York in 1918. He was this physicist's meant by them exclusively waves. While working at Princeton University, Feynman was involved in early atomic weapons research. In 1943, he went to Los Alamos National Laboratory in New Mexico, as the youngest member of the Manhattan Project. There he helped calculate the explosive power of atomic bombs and launched a primitive computer system to analyze the huge amount of data involved in this project. In 1950, Feynman became a professor at the California Institute of Technology. There he and Murray Gell-Mann tried to describe a small force inside atoms. This work explained what happens when radioactive atoms decay or are destroyed. Feynman's lectures at the California Institute of Technology served as inspiration for a new generation of particle physicists. And his books on a variety of topics impressed the general public. Feynman continued to work at the California Institute of Technology until his death in 1988. A field in physics is a region of space in which some physical influence on bodies is manifested. Examples of this are gravitational and magnetic fields. Consequently, field theory describes how these fields behave and how bodies interact with the fields they are in. In the late 1920s, one of the founders of quantum mechanics, Paul Dirac, published several articles showing that quantum theory can be combined with James Clerk Maxwell's theory of the electromagnetic field, as well as with Einstein's theory of relativity. He created the first quantized field theory that described the interaction of electrons and photons, particles of light. In 1949, several physicists, including the great Richard Feynman, created quantum electrodynamics. Later, this theory was used to combine the electromagnetic force with another of the four forces of nature, the weak interaction. This development became known as the theory of electroweak interactions. A separate quantum field theory, known as quantum chromodynamics, was created to describe strong interactions. Only the fourth and last force of nature, the force of gravity, still manages to resist attempts to become quantized. Quantum field theory applies the strange laws of quantum physics not only to a solid particle, but also to fields, describing the basic forces of nature. This is not an easy theory. When two quantum objects, such as electrons or photons, come into contact, their quantum states, mathematical information describing their quality, connect or intertwine. Then their fates remain intertwined, no matter how far they advance in the future. Because it is easy to believe that two objects having a common past, during their interaction, will in some way affect the quality of each other. The result of this interaction will be noticeable later, when we check these particles. However, entanglement theory can be much stranger. In the quantum world, bodies are capable of displaying two or more incompatible qualities at the same time. For example, rotating in opposite directions at the same time. This is called an overlay. For example, if one photon is intertwined with another, it can infect it with its overlap, so that both will be in overlap. However, by looking at one of them, we force the photon to decide which way it will move. Well, since it is intertwined with its partner, we will force the other photon to make the same choice. This will happen instantly, even if the two photons are now millions of miles apart. Subatomic particles are connected to each other, even if they are separated by huge distances. Will we ever be able to unravel quantum entanglement? Someday quantum entanglement will allow objects and people to teleport over vast distances. This is an attempt to describe in a unified theory the work of all four main forces of nature and the relationship between all elementary particles. In physics, forces can be characterized by fields that transmit interactions between particles. They are known as field theory. So, in 1915 Albert Einstein developed the general theory of relativity, the theory of the gravity field. At subatomic distances, fields are characterized by quantum field theories that apply the ideas of quantum mechanics to the basic fields associated with the other three forces, the electromagnetic force and the strong and weak interactions. Now the goal of scientists is to understand whether quantum chromodynamics, the theory of the field of strong interactions, can be combined with the theory of electroweak interactions, which describes the electromagnetic force and weak interactions. The result of this will be the so-called grand unification theory. However, a successful grand unification theory will still not include the force of gravity. The problem is that physicists still don't know how to formulate a real quantum field theory from the theory of gravity. One possible candidate for such a theory of everything is the so-called string theory, but we are still far from understanding whether it is true or not. Everything is connected in the universe. It's easy to say, but it's very difficult to figure out how to prove it. All the stars that we observe in the sky are part of a system called the Milky Way galaxy. The Milky Way consists of hundreds of billions of stars and hundreds of billions of galaxies scattered throughout space. Most of them are in groups held by gravity. The cluster of galaxies resembles a huge swarm of bees, which moves as a whole. The study of the movement of groups of galaxies shows that over time they move away from each other. The best proof of this is the red shift of light from distant galaxies. The red shift, literally the reddening of galactic light, shows that each cluster is moving away from another cluster and there is no center for this expansion. This is explained by the general theory of relativity as a result of the expansion of space between groups. So, a long time ago, all the galaxies, stars and matter in the visible universe were gathered in one place, in a bunch of hot energy the size of a grapefruit, called the Big Bang. By measuring the speed at which galaxies are moving away from each other today, astronomers estimate that the Big Bang occurred 13 7/10 billion years ago. Imagine a grapefruit that weighs as much as the entire universe and is heated to billions of degrees. Since the amount of light emitted by a star depends on its mass, astronomers can weigh galaxies by measuring the brightness of stars. Since the force of gravity affects the movement of things, astronomers can weigh the universe by studying the movement of galaxies and the rate of expansion of the universe. All the bright stars in all the galaxies make up less than 1% of the mass needed to explain how galaxies move and how the universe expands. Studies of how the atoms and particles that make up you and everything around you occurred during the Big Bang show that there may be about 4 times darker atomic matter in the clouds of gas and dust between the stars. It is called baryonic matter because it consists of baryons located in the atoms of large particles. It is now believed that baryonic matter makes up about 4% of the mass of the universe. The nature of the motion of galaxies shows that there is 4 or 5 times more non-baryonic dark matter consisting of smaller subatomic particles. However, about 74% of the mass needed to calculate the expansion of the universe has not yet been found. There is not enough light from the stars in the universe to calculate its weight. Most of the matter in the universe is too dark to be seen from Earth, and huge areas of it seem completely invisible. The Big Bang theory includes events called cosmic inflation. Before the universe swelled into an incredibly hot fireball, which has since cooled down and turned into a galaxy and stars, it was concentrated in one single point. Quantum uncertainty allows a tiny clot of energy to arise completely out of nothing. However, if such a bubble contains a form of energy known as a scalar field, it can act as anti-gravity, causing the bubble to expand at maximum speed until it reaches a volume of about 10 centimeters in diameter. Roughly speaking, the size of a grapefruit. Before the field gives up its energy in the form of heat and the effect of anti-gravity is completed. At the end of the process, the inflationary model of the universe is a fiery clot of energy, a ball the size of a grapefruit, which continues to expand, but more calmly, as a result of the push received from inflation. It's a Big Bang. The theory of cosmic inflation suggests that a certain pattern of waves was imprinted on the spacetime of the grapefruit stage. These oscillations provided the oscillations by which galaxies and galaxy bundles could increase by gravitational fusion as the universe continued to expand. Nothing can move faster than light, only spacetime itself. During the period of cosmic inflation, the expansion of the universe broke the record of cosmic speed. The universe we live in is the best fit for our lives. If there were a little more gravity, the stars would be smaller. They would use their nuclear fuel faster and would burn up before complex life forms like us could arise and evolve around them. According to the anthropic principle, we can use the fact of our existence to predict the significance of certain qualities of the universe, such as the force of gravity. It is known that in the 1950s, astronomer Fred Hoyle used this argument to predict certain qualities of the nuclei of carbon atoms, since our form of life depends on carbon. And without these qualities, carbon would not be able to be created inside stars and we would not exist. Later, Hoyle's assumptions were confirmed by experiments. Then the question remains, why is the universe, like the porridge of a bear cub in the fairy tale Goldilocks and Three Bears, just right? Some believe this means that the universe was intended for us. Others believe that there are many universes, and there is life only on those that are similar to ours. The place of the Earth in the universe is like the porridge of a bear cub. It's not too hot and it's not too cold. It's exactly what it should be. Is this a pure coincidence? What form does the universe have? Topology is the science of shapes and how one shape can transform into another without breaking it. It is believed that a topologist is a person who is unable to distinguish a donut from a coffee cup. If the donut was made of rubber, you would be able to stretch it and shape it into a cup. The inner ring becomes the handle of the cup, and the rest of the donut turns into the body of the cup. Most astronomers believe that the universe is infinite. However, if it were finite, it could have the shape of a very large donut. If it were so, looking in one direction around the donut ring, you would see the same galaxies that you would see looking in the other direction around the ring. In a more complex topology, imagine a cube in which opposite faces are connected. If you travel on a spaceship through the roof, you will return to the cube through the floor. Even if the universe is finite, observations show that its topology is not so simple at all. The study of the radiation left over from the Big Bang suggests that the universe may have the shape of a five-dimensional dodecahedron, very similar to the three-dimensional arrangement of fragments on a soccer ball. For topologists, coffee and donuts are inseparable. For them, a donut and a coffee cup have the same shape, only the lengths and angles of their sides differ. It is believed that our universe originated when cosmic inflation occurred in a tiny part of empty space. Even today, dark energy causes the universe to expand faster and distributes matter in it with an even thinner layer. As a result, only empty space will remain. Then inflation will be able to create even more worlds in this empty space. Consequently, our world is one of many that arose in the previous phase of the process called infinite inflation, which has neither end nor beginning. So an infinite number of bubble universes can be created. Then there is no reason to expect that the laws of physics will be the same in every world. Some universes will be a suitable place to live, others will not. This explains the puzzles of anthropic cosmology. It also means that there will be worlds in which every conceivable possibility actually happens. Worlds where the South won the American Civil War and worlds where dinosaurs never died out. Perhaps there are other lands similar to ours in other worlds. Dark energy accelerates the expansion of the universe. If this continues, and there is no reason to believe that this will not happen, then the expansion will happen faster and faster over time. At first, it will not affect matter directly. Within galaxies, stars will continue to be born, live their lives and die. However, when the matter that stars are made of is used up, galaxies will weaken and more matter will accumulate inside various forms of dead stars, white dwarfs, neutron stars and black holes. However, While this is happening, the bundles of galaxies will scatter faster and faster, disappearing from each other's sight. Our own Milky Way galaxy is part of a small group called the local group. In a couple of 100 billion years, a period about 10 times the current age of the universe, nothing visible will remain outside the cosmic archipelago. Eventually, the cosmos will expand so fast that it will overcome the force of gravity and other forces, and material objects will be torn apart. The result of this will be a rapidly expanding cosmos in which matter is distributed so thinly that it is, in fact, empty. These are ideal conditions for the birth of one or more new worlds due to inflation. It will take a few more years, to be exact, 1 and 11 more zeros, but eventually the forces that created the universe will tear it apart. The ekpyrotic theory owes its name to the Greek word meaning born in fire. Another name is the Phoenix universe. According to this idea, our universe is one of two three-dimensional worlds separated from each other by a tiny space, the mini-diameter of an atom, in the fifth dimension. In fact, this is the fourth dimension of the cosmos, but the name of the fourth dimension has already been confirmed by time. Every point in our cosmos is adjacent to a point in another world. Currently, the two worlds are slowly moving away from each other. In addition, each world expands by itself, diluting its contents. As a result, they will turn into an empty expanding space. By that time, the original source force will bring both worlds together again along the fifth dimension. The energy released by the collision of the two worlds will turn into matter, creating a new Big Bang. Due to quantum effects, different parts of the two worlds will touch each other at slightly different times, creating vibrations that are the seeds from which galaxies grow. Then the worlds will move away from each other and the whole process will repeat. It happens all the time. This is the main alternative explanation for the Big Bang, and it does not require the first phase of inflation. Give me your five-dimensional spacetime, and I'll give you an extra-erotic universe in which we oscillate back and forth with an invisible partner universe, involved in a constant sequence of Big Bangs. Planets created from a cloud of particles as scattered as smoke. This cloud orbits the Sun in the form of a disk, like the rings of Saturn. The particles begin to stick together as they all move along the same path around the Sun and often crash into each other. As a result, they become quite large and begin to attract each other by gravity, continuing to grow. Larger fragments absorb smaller ones and become early planets. These large fragments crash into each other, split and reconnect many times until they calm down and turn into planets, such as we see them today. No one knows exactly why there are 4 small dense planets next to the Sun, and 4 large gaseous ones further away from it. Most likely, it was difficult for planets near the Sun to hold on to gases that were carried by solar radiation. On the contrary, gas giants could accumulate ice particles beyond the zero-temperature boundary. That is, at such a distance from the Sun, where not only glacial water, but also other frozen substances, such as methane and ammonia, do not melt. Giant planets grow out of tiny dust particles. The planet Earth, the Sun and the rest of the planets of the solar system emerged from a huge cloud of dust and gas, which slowly collapsed under the influence of the forces of their own gravity. Our planet never stands still, and even the continents are constantly drifting, moving in a slow dance on the surface of the Earth, at about the same speed as nails grow. In the history of our planet, there periodically come times when this dance brings all the continents together, and then they create a giant supercontinent until they go their separate ways again. This happened about 1 3/10 billion years ago, when the radiation was formed and repeated 250 million years ago with Pangea. In itself, the idea of the mobility of continents is quite old. In 1596, noticing the compatibility of the coast of Africa and South America, the Belgian cartographer Abraham Martel suggested that America was forcibly pushed away from Europe and Africa by earthquakes and floods. However, it took another 300 years before the German scientist Alfred Wegener put forward the theory that the continents are constantly moving. However, without a mechanism explaining how this is possible, this idea was not really accepted until the early 1960s. By this time, new geophysical facts showed that the movement of the continents was accompanied by the expansion of the seabed and was controlled by currents in a partially molten layer under the solid crust and the uppermost part of the mantle. The ground under our feet is not quite solid, and it is constantly moving. As you probably guessed, the snowball Earth theory suggests that in ancient times the Earth was covered by glaciers, making it look like a giant snowball. Proponents of this theory, including the American geobiologist Joseph Kirsching, who coined this term, believe that during the cryogenic period, about 630 million years ago, a weak sun and a low concentration of greenhouse gases in the atmosphere led to a sharp drop in temperature on the planet. The key point of the theory is an unusually low concentration of greenhouse gases, and there are a lot of options for its occurrence. One option is that the connection of continents near the equator provided ideal conditions for the development of large-scale tropical erosion, in which carbon dioxide in the atmosphere reacted with rocks, creating solid minerals. As a result, the concentration of gas in the atmosphere has sharply decreased. As soon as the planet was enveloped in ice, it became difficult for it to warm up to the temperature necessary for melting ice, because the white surface of the planet reflected most of the solar radiation back into space. The only possibility was an increase in heat from the sun or an increase in the level of carbon dioxide in the atmosphere, perhaps because of the gases released during the eruption of volcanoes. The white surface of the frozen Earth reflected the sun's heat back into space, maintaining cold temperatures. James Lovelock is one of the few independent scientists of our time. He hadn't worked at a university or a government laboratory for 40 years. Direct and radical, Lovelock is both a scientist, an inventor, and a visionary. His most famous theory is the Gaia hypothesis, a description of the way the Earth self-regulates. It is not fully accepted by the scientific community, which has complaints about the methods by which Lovelock tested his ideas. Although this theory is very convincing, it is unknown whether the Gaia hypothesis will ever become a useful tool for other scientists. James Lovelock was born in the town of Leck, north of London in 1919. He studied chemistry in Manchester until he transferred to the National Institute of Medical Research in 1941. Most of his early work at this institute was related to military developments. So he invented an underwater monitor for measuring blood pressure and a device for measuring the speed of sound. After working at the institute for 20 years, Lovelock went to work at NASA. There, his knowledge was used to create detectors that could analyze the composition of rocks and the atmosphere of the Moon or another distant planet. Many of the space research rockets packed with Lovelock devices have been tested to detect evidence of life. Lovelock realized that the most obvious evidence of life on another planet is its dynamic atmosphere with an ever-changing composition. The atmosphere of a dead planet remains unchanged. Thinking about how life has changed the Earth's atmosphere prompted Lovelock to create the theory of Gaia. Lovelock left NASA in 1964. He returned to the UK and became an independent scientist and inventor. In 1979, he published his first book under the simple title Gaia. Soon it was accepted by the community of experts on environmental issues, but rejected by many scientists who argued that it was based on the philosophy of the new century, and not objective scientific research. However, many believe that Gaia's theory has proved useful, launching a multi-year series of studies and controversies. In 2000, Lovelock again justified his reputation as a free scientist when he announced that nuclear energy was the best way to regulate climate change. This time the criticism came from environmentalists. Global warming is a rather harmless name for the continuous and inevitable warming of our planet. The Earth is an incredibly dynamic planet, whose climate, throughout its history of 4 6/10 of a billion years, has constantly experienced sharp temperature fluctuations. We live in a mild interglacial period. Between the last ice age, which ended about 10,000 years ago, and the future ice age. Usually, during the interglacial period, the level of carbon dioxide, the main greenhouse gas that keeps the cosmic cold unchanged, stopping the solar heat, is about 280 millions. Now, due to pollution due to the 200-year period of industrialization, it has reached 385 million shares and continues to grow. Although there are skeptics who refuse to confirm the human factor of global warming, the link between carbon dioxide emissions and the warming of the planet is not new. In the 1890s, the Swedish chemist S. Svante Arrhenius calculated that an increase in the concentration of carbon dioxide in the atmosphere by half would lead to a rise in temperature throughout the planet by 4 degrees Celsius. So far, our planet has warmed up by 0.74 of a degree Celsius, and Arrhenius' prediction is likely to come true around the 2100th year, provoking chaos and environmental degradation. Some people like warmth, but global warming will make the climate not warmer and sunnier, but more severe. Get ready for strong winds and heavy rainfall. It is believed that the temperature on Earth depends on the amount of greenhouse gas released by industrial enterprises. The theory of catastrophes is based on an idea beloved by the creators of Hollywood blockbusters. The Earth periodically experiences unpredictable short-term cataclysms with global consequences. Such a picture of the world is born of the idea that catastrophes are the action of God, who sends them on people as punishment. Such ideas are borrowed from the biblical tales of the Day of Judgment and disasters, such as the flood. In the 18th and 19th centuries, the theory of catastrophes flourished as a scientific theory, when naturalist philosophers argued about the history of the Earth, marked by catastrophic events that occurred over a period of only a few thousand years. Probably the most famous proponent of the theory of catastrophes was the French paleontologist Georges Cuvier, who linked catastrophes with mass extinctions. In the middle of the 19th century, the theory of catastrophes was replaced in scientific circles by uniformitarianism, a concept introduced by the Scottish polymath James Hutton and spread by the English geologist Charles Lyell. In contrast to the theory of catastrophes, this concept recognizes that the history of the Earth is marked by successive, ever-increasing changes involving the same physical processes that we observe now in the world around us. About 65 million years ago, most of the giant reptiles suddenly became extinct. The list of causes of this disaster extends from the fall of a large meteorite and volcanic eruptions, to the disappearance of ferns that served them as food. The Gaia hypothesis was formulated in the 1960s by the English scientist James Lovelock, who called the Earth a living self-regulating organism. Although this does not mean that our world is actually alive. It consists of complex, interconnected interactions of life and the physical environment, the atmosphere, oceans, polar ice, and rocks under our feet. According to Gaia's hypothesis, these relationships work together, keeping the Earth in a state necessary for the preservation of life. This balanced state, sometimes called homeostasis, is also characteristic of living organisms themselves, which are able to manage their internal processes while maintaining the status quo. In defense of his ideas, Lovelock pointed to the extraordinary stability of the temperature of the Earth's surface for a long time, despite the growing increase in solar radiation. He also noted the constancy of the salinity of the ocean and the composition of the atmosphere, despite the presence of many factors that could and should have brought these parameters out of balance. The Gaia-Lovelock hypothesis has been sharply criticized, especially by biologists. However, the idea that life plays a key role in maintaining the habitability of our world continues to arouse both interest and support among eminent scientists. Lovelock's Daisy World is a simple model of how life on Earth reacted to changing conditions on the planet's surface. Earth may be a rare example of a home for intelligent life. It took more than 4 billion years of evolution for our civilization to emerge on a calm stable planet orbiting a calm stable star. The Sun is an unusually stable star, and it has been a reliable source of heat throughout the evolution of life on Earth. Jupiter protects the Earth from comet bombardments. Our giant neighbor sucks in these icy bodies before they have time to get to us. But even in such conditions, several major terrestrial catastrophes, including the extinction of dinosaurs, are associated with the fall of comets. Without Jupiter, such falls would be so frequent that intelligent life would not have time to evolve on Earth. The huge moon is also extremely important. It stabilizes the axis of the Earth and does not allow it to wobble from side to side, like a spinning top. The periodic forces launched by the moon inside the Earth retain its heat and maintain magnetic fields that protect us from harmful cosmic rays. The same forces trigger the ocean tides, which played a huge role in the emergence of life on land. Life on Earth has become possible thanks to many happy events. For example, our giant moon helps us in many ways. 100 years ago, a Swede from Venta Arrhenius suggested that life in the form of spores could persist in space and spread from one planetary system to another. According to Arrhenius, randomly moving spores fly out of the planet's atmosphere and spread throughout interstellar space, thanks to the weak but constant radiation pressure released by starlight. The modern version of the idea of panspermia originates in observations of prebiotics in interstellar clouds. Obviously, some substances from this raw material, for example, amino acids, fell on the young Earth and started the process of life on it. Some researchers, especially the late Fred Hoyle and Chandra Micromason, argued that not only complex organic substances, but even full-fledged living organisms, such as bacteria, could develop in space on the surface of dust grains, and then hit the Earth through a colliding comet. There is also a possibility of ballistic panspermia, when stones from one planet were squeezed into space and traveled to another planet. The discovery on Earth of meteorites from the surface of Mars means that we may have originated from Martian bacteria. Did life on Earth originate from outer space? Did Earth spores sow life on other planets? A person suffering from angina or from algia is infected with bacteria that spread through these parts of the body. The disease is treated with antibiotics. A small dose of the drug prevents the reproduction of bacteria, and the infection almost completely disappears. However, in a few days it may return, since bacteria that are immune to antibiotics will take the place of those destroyed by treatment. The transition from a drug-susceptible bacterial population to a non-susceptible population is the most obvious example of natural selection in action. Drug resistance is passed on to the next generation of bacteria, and as a result, this trait becomes inherent in all members of this population. This process occurs in all creatures capable of transmitting certain properties to their offspring during reproduction. However, errors in the process ensures that each individual descendant is unique, albeit in the smallest details. Evolutionary changes usually take much longer. But the same process that changes a group of bacteria explains the evolution of life on Earth for 3.5 million years. Natural selection ensures that life, in an attempt to survive, adapts to different conditions. The theory of natural selection states that species evolve to overcome difficulties in their habitat. The theory of evolution as a result of natural selection is a powerful blow to religion. It explains the emergence of complex organisms that were previously thought to have been created by the Creator. Apparently, the properties of living beings benefit their owners. When a cat eats a mouse, it uses sensory systems, eyes, whiskers and so on, muscles, paws and digestive system, and all in order to survive another day. These properties appeared as a result of natural selection. Thus, natural selection leads to the appearance of qualities that help living beings. However, these same organisms sometimes show altruism. One individual sacrifices himself to save the others. Altruism contradicts natural selection, and it was previously believed that sacrificial behavior was for the benefit of species. However, no mechanisms capable of explaining natural selection at the level of all organisms have been found. Altruistic behavior makes more sense if you look at the benefits it brings to the genes. Close relatives, for example, two sisters, have at least several identical genes. One sister can sacrifice herself to ensure the survival of the other. A deceased sister cannot pass on her genes. However, the genes she shared with her sister will survive her death, and it will benefit her selfish genes to die protecting her sister. The selfish gene theory originated in the 1960s, but the novelist Samuel Butler managed to express this idea back in the 19th century, saying, which appeared first, egg or chicken? A chicken is most likely just a means by which an egg produces another egg. Professional scientists have their favorites and heroes who have served as an example for them. But perhaps Charles Darwin's theory of evolution by natural selection has done more than any other scientific work. Thanks to her, ordinary people took a different look at their place in the world. Charles Darwin was born in 1809 year in a famous family. His maternal grandfather was Josiah Wedgwood, who made a fortune in the mass production of fine porcelain. Darwin's paternal grandfather, Erasmus Darwin, a hard-drinking doctor and poet, wrote a book about evolution himself in the 1790s. Erasmus believed that animals changed their shape under the direct influence of the environment. This idea was later developed by Jean-Baptiste Lamarck, and is now better known as Lamarckism. At the age of 16, Charles Darwin was sent to study medicine in Edinburgh. There he became interested in Lamarckism, as well as the works of geographer Alexander von Humboldt and geologist Charles Lyell, who suggested that the Earth is much older than is commonly believed. In 1831, Darwin boarded the Beagle ship for a fee. On it he made a trip to the shores of South America. What he saw during the 18 months of the journey made him formulate a theory of evolution by natural selection. However, he decided to keep it a secret until the end of the 1850s. In 1858, while working on a book on this topic, Darwin received a letter from his colleague, the naturalist Alfred Wallace. Wallace, working in Indonesia, developed the same theory. This prompted Darwin to publish The Origin of Species the following year. His work blew up the scientific community. Darwin found himself in the middle of an endless public debate on this topic, and to avoid them, he returned to a townhouse in Kent. There he wrote several more books, most about strategies for the origin and function of emotions. Charles Darwin died in 1882. We all think we know what information is. But this theory reveals its true essence and shows how to formalize and convey it as quickly and flawlessly as possible. Now information theory supports a lot of everyday technologies, from high-definition digital television and DVDs, to mobile phones and barcodes on supermarket products. The origins of this theory lie in the work of Claude Shannon, a brilliant young American engineer who developed an accurate mathematical theory of information in the 1940s. The main unit of information, by his definition, was the true-false state, the so-called bit, which can take the value either 1 or 0. With the help of this mathematical definition, Shannon was looking for ways to quickly, but at the same time flawlessly transmit information, even in the presence of interference. The results of his research form the basis of so-called compression algorithms that allow you to burn entire movies to DVD or transfer them over the internet. This theory has also led to so-called error correction codes, thanks to which phone calls across the Atlantic remain crystal clear, and barcodes in the supermarket are readable, even on crumpled peanut packaging. Information theory can turn a human voice, a picture, or a number into ciphers consisting of 2 digits, 1 and 0. These codes are easier to store and transmit. Compared to modern computers, devices from 5 years ago seem like museum exhibits. Extraordinarily powerful, with huge memory and hard drive capabilities, our computers continue to grow, while prices remain unchanged. This incredible rate of improvement was first determined in 1965 by Gordon Moore. In an article in Electronics magazine, he predicted that the number of electronic components that engineers will be able to cram into each integrated circuit will increase from about 50 to 65,000 in 10 years, that is, roughly speaking, it will double every year. In 1975, Moore adjusted his forecast, giving this speed a more modest appearance, and now it bears his name and means doubling computer power every 2 years. Since then, Moore's law has proven to be surprisingly reliable and is likely to remain so. At least for the next decade. Not least because he set the bar that microchip manufacturers strive to achieve. But in the end, the laws of physics will force this law to give up. There are limits to how small electronic components can be. Moore himself believes that this will happen around 2025 year. Are you going to buy a computer? Better wait, they are constantly getting faster, better and cheaper. This is a theory about conciseness that deserves every respect. And there are reasons for that. According to the 14th century English logician William Acom, elegant explanations are more likely to be correct than tortuous and messy. He advised making fewer assumptions necessary to complete the work, or, as the authors later came up with, shaving them off, figuratively, reducing them to the utmost minimum. At the heart of this is the idea that nature prefers simplicity to complexity. It is not difficult to find examples of this. In the Middle Ages, astronomers, explaining the movement of the planets, tried to complicate their point of view about the Earth as the center of the solar system. However, it was worth simply putting the sun in the center of the system, and all this complexity turned out to be unnecessary. Occam's theory suggested that this heliocentric point of view was more correct, and it really turned out to be true. However, it is often not so easy to find a simple explanation. For example, is Einstein's law of gravity really simpler than Newton's law? Even today, attempts to turn Occam's razor into a rigorous mathematical rule run into a contradiction. Keep it simple, that's the essence of Occam's razor. Realizing this, shorten the theory, leaving nothing but its basic elements. Every time we copy habits, skills, stories, songs or any information from person to person, we are dealing with memes. The idea of memes, along with scientific theories, is also a meme in itself. The meme originated from the theory of universal Darwinism, the idea that when any information is copied, changed and selected, there must be an evolution. The most well-known replicator is a gene, but in 1976 Richard Dawkins declared that culture consists of a second replicator, and he called it a meme. People copy memes, including ideas, skills, and behaviors, through imitation and learning. Copied, they change by making mistakes, intentionally allowing changes or through a creative combination, and choose which meme to choose and transmit. The science of memetics studies how memes spread, why some succeed and others fail, and what are the consequences of this for the evolution of culture. In general, some memes are distributed because they are useful or convenient for us. For example, the sections of science and medicine, financial institutions, arts and music. Others spread like viruses, even if they are useless. We humans are the tools of memes, and they use us to survive. All the thoughts in your head are competing with each other. They want you to tell someone else about them. They want to get into another head and spread even further. This is an old problem that concerns everyone, from warlords to card players. What strategy should we choose if we don't know what the opponent is thinking? The solution to such problems is the reason for the section of applied mathematics called game theory, which, despite its names, deals with something much more serious than a fun pastime. The first understanding of its essence came in the 1920s, when mathematicians invented rules for so-called zero-sum games, where one person's winnings are equal to another's losses. Known as the minimax theorem, this rule advises choosing the strategy that gives the best effect under the worst circumstances. However, in real life, most games are not zero-sum games, and some strategies can lead to both sides winning something and losing something. In 1950th year, the American mathematician John Nash managed to develop the minimax theorem and include these non-zero-sum games in it, greatly expanding the scope of game theory. For example, evolutionary biologists have used it to understand why animals prefer to cooperate rather than fight each other, and psychologists have used it to study the behavior of criminals in a law-abiding society. Everything from war to business is a game. And game theory is the kind of math that can help you win. At a party, you are talking to a complete stranger and suddenly discover that you have a mutual friend. You exclaim, "The world is small." Of course, this is true, and attempts to explain it have given rise to a new scientific discipline known as the theory of the small world, which finds explanations for topics from the spread of diseases to the consequences of globalization. At the center is the idea of a network created from interconnected elements, from friends and neighbors to computers or multinational companies. Such networks are usually a combination of close connections, for example, families who live in a small village, plus a few random long-distance connections, for example, villagers who have to travel a lot for work. Mathematicians have shown that one handful of these random connections is enough to short-circuit vast networks, turning them into small worlds where everyone is connected to everyone through relatively few intermediaries. Indeed, research suggests that every person in the world can be connected to another person through about 6 intermediaries. In our world where everything is interconnected, one minor event can have serious consequences affecting millions of people. You leave home 5 minutes late and miss the train to the airport. Arriving at the airport, you are late for your flight and find out that the next flight will be only tomorrow. A 5-minute delay turned into the loss of a whole day. This is an everyday example of what mathematicians call a nonlinear phenomenon, where minor events do not necessarily have minor consequences. Chaos theory focuses its attention on such situations, the outcome of which is often not random, unpredictable. One well-known example is the weather, where nonlinear effects lead to the appearance of small observational errors, which eventually grow to the point where any hope of making a reliable forecast is dashed. Forecasters even talk about the butterfly effect, in which the flapping of a butterfly's wing is enough for any prediction to undergo significant changes. Chaos theory provides the tools necessary to determine the difference between a seemingly random and therefore truly unpredictable phenomenon and those that are rather chaotic. But there is some hope that they were predicted correctly. According to chaos theory, one tiny mistake can result in a serious event and even a catastrophe. Every living being is born with certain properties and acquires other properties during life. Acquired properties include deformities such as scars from disease, smallpox, and scars from healed wounds. Physical development, such as increased muscle volume due to exercise, and skills acquired in the course of study, such as the ability to read. From the very beginning, as soon as human thoughts began to be recorded, it was believed that some of these acquired qualities were inherited by the next generation. A frequent example of this idea was the fact that physically strong blacksmiths most often produce strong offspring. This idea can be found in the works of the ancient Greek philosopher Plato. In the 19th century, the French biologist Jean-Baptiste Lamarck described the inheritance of acquired qualities in his book, Anticipating Darwin's Theory of Evolution. A famous example of Lamarck's theory concerns the giraffe. For generations, giraffes could reach trees in search of food by slightly stretching their necks. If the acquired elongated neck of each individual animal was inherited by its descendants, over time giraffes developed a long neck. If there is not enough grass for everyone, why not try the leaves? That's how giraffes got a long neck. It didn't happen the way Lamarck intended. The ancestors of man separated from the great ape about 6 million years ago. Between that period and about 2 million years ago, our ancestors lived in Africa. Then the first people, called Homo erectus, came out of Africa and settled Europe and Asia. Up until about 30,000 years ago, Homo erectus and his descendants, known in Europe as Neanderthals, conquered all 3 of these continents. The question is whether modern humans descended from the kind of anthropoids that lived in Africa and Eurasia, within the framework of an idea called the multizone hypothesis. Or we all descended from a single ancestor in Africa, who spread around the globe during the second wave of migration that destroyed the local humanoids. The fossil evidence has been mixed. Then, in the 1980s, genetic evidence appeared. If the multizone hypothesis is correct, the genes of modern humans must have a common ancestor. In fact, the number of differences between our genes is very small. The degree of similarity requires that we have a common ancestor whose age is much less than 2 million years, probably about 100,000 years. During this time, evolution has only slightly changed our DNA. Now everything points to the fact that modern people are relatives of one African ancestor. Genetics proves that all 6 and 7/10 of a billion people living today descended from just a few thousand early Africans. The term sociobiology entered the popular consciousness in 1975, after the publication of the book of the same name by Harvard biologist E.O. Wilson. Wilson defined sociobiology as the biological study of social behavior. Wilson wrote about the emerging field of biological research, which was looking for answers to many questions. Why are male and female individuals different? What is the function of mating systems? Why are some species monogamous and others not? Why do animal communities have such a structure? For example, groups of chimpanzees consist of male relatives and young females who leave home. While in baboons, it is the young males who leave their families. Sociobiology also explores the causes of such phenomena as camaraderie, altruism, territoriality, and tries to answer the question of why some species live in large groups, while others have hermits. However, Wilson has moved a step forward. In the last chapter of his voluminous book, he offers several biological explanations for human social behavior. This chapter provoked protest from those who decided that it hurt their political views. If you think that human society is the pinnacle of sociobiology, think again. Bees, ants, and other insects live in large groups, but for completely different reasons. Residents of Olga are all sisters who work for their mother, the queen. The purpose of their existence is to take care of their newborn sisters so that the queen has as many daughters as possible. Grammar is the key to understanding human language. Many animal species have a developed system of signs that they use to communicate. But they do not have subordinate clauses, moods, cases, and prepositions that make up grammar. Human language is infinitely expressive and can be used to discuss and ponder abstract concepts. Where did the language with grammar come from? The changes required for this were in the software of the brain of our ancestors, and it is impossible to study it. However, we have two indirect proofs. The first is the time when human brains appeared, working the same way as ours. It happened a little more than 100,000 years ago, and the brains belonged to people who came from Africa and gave birth to a talkative primate called Homo sapiens, that is, us. From an anatomical point of view, their brains were identical to ours. This means that they had the same linguistic capabilities as us. However, the key change came later and affected not just the bare anatomy, but how we use our brains. Archaeologists have discovered a lot of elegant tools, jewelry, and other objects, about 30,000 years old. Language is what distinguishes humans from animals. Only we know how to express our thoughts. Now the only thing we have to do is figure out what to say. Only humans have brains big enough to cover all the many ways to say the same thing. Like the tattoos of a man with a devilish image of himself on one shoulder and an angelic version of himself on the other, Sigmund Freud's theory of psychoanalysis asserts that the human mind is torn apart. Our ego is constantly striving for a balance between the needs of the superego teaching it and the desires of the insatiable animal subconscious. The central idea of psychoanalysis is that most of this conflict is hidden under the crust of consciousness, only occasionally breaking through in the form of a nervous tic or a Freudian reservation. Sex also plays a big role in this theory. In particular, Freud believed that the source of physical conflict is the sexual fantasies of childhood. The most famous example of this is the Oedipus complex, the idea that children lust after their parent of the opposite sex and zealously wish for the death of a parent of the same sex as them. Perhaps you will say that you have never had such desires. Your denial will be a great example of suppression, one of the many defense mechanisms that, according to Freud, we use to tame uncomfortable desires for us. Such mental maneuvers will save our reputation for a short time, but in the end they can lead to confusion and make clients a psychoanalyst. The ink spot test is a technique used by psychoanalysts. Patients describe the shapes they see in the spots, thereby revealing their suppressed emotions. If you can't see anything but an ink stain, then maybe you're really in trouble. Behaviorism, from the English behavioral behavior, dominated the science of psychology for half a century, although it ignored all the concepts of reason and consciousness, and refused to take into account feelings, thoughts and desires. Instead, he focused his attention on behavioral patterns that could be measured in the laboratory. Behaviorism appeared in 1913 year, when psychologist John Watson stated that the degree of human scholarship can be studied in the same way as the famous Pavlov's dogs, which salivated at the sound of a bell, which they associated with eating. He argued that the development of a suitable conditioned reflex can be used to turn your children into any person you wish. B.F. Skinner, another American psychologist, came up with the development of an instrumental conditioned reflex, in which rats were rewarded for a certain behavior and punished for another, teaching them to press levers, run through mazes. He found that praise is much more effective than punishment, a key principle for parents and teachers. Skinner founded his own school of radical behaviorism, claiming that all our actions are defined. He also reflected on a utopian society based on the development of conditioned reflexes in all citizens. Behaviorism explains how people learn from their experiences, both good and bad. Cognitive psychology considers people as information processing systems and studies how we think, perceive, learn and remember. The word cognitive comes from the Latin word to think, and the term cognitive psychology was introduced by Ulrich Nieser in 1967. It was an interesting transition from the dominant behaviorism, which limited all research to mental processes. The new cognitive psychology studied internal mental events and turned into a rapidly developing science of artificial intelligence. In this new science, the mind was likened to software, and the brain to the equipment of a biological computer. Human actions, decisions and thoughts were forms of information processing and depended on the data coming from the senses. For example, the study of the visual system of the brain has shown how information coming through the eyes is processed by layers of eye cells, the midbrain, the sensitive area of the cerebral cortex, and sent to areas of the brain capable of recognizing objects or controlling actions and speech. Is it a brain or a computer? Cognitive psychologists say that there is almost no difference, and the brain is a mechanism for processing information. Genes control most of the basic functions of life. When they go astray, we can develop diseases from Alzheimer's to cancer, and we can pass on inherited diseases to our children. Genetics in medicine tries to find the best, if imperfect, methods of treatment by investigating the genes responsible for the disease. It sounds pretty simple. Find the dubious genes responsible for the disease, banish them and insert fresh copies. For a while, this is exactly how genetics was represented in medicine, but the reality turned out to be more complicated. While some hereditary diseases are the result of a single faulty gene, most diseases arise from complex interactions between a set of genes. Restoring even one gene turned out to be an incredibly difficult task, and to date, not a single person has been cured of a genetic disease. Genetics has been more successful in creating drugs that regulate gene-related diseases. For example, the drug Herceptin was created by identifying genes involved in certain forms of breast cancer. But even such drugs have very limited effects and are another example of the fact that genetics in medicine has not justified the hopes associated with it. Perhaps one day gene therapy will become a panacea. But first, geneticists need to understand exactly how the DNA strand builds the human body. Having learned this, we will be able to notice when it fails and fix it. Proponents of alternative medicine, from acupuncture to yoga, see it as a therapy that can be used alongside traditional medicine. For her opponents, is this a bunch of unproven tricks that take over patients, while the main burden falls on traditional medicine? There is some truth in this. Some conditions that seem to respond well to additional therapy, such as pain and depression, are associated with a powerful placebo effect, in which patients believe that they are getting better after, in general, useless treatment. Scientific experiments in which such methods of treatment were tested gave contradictory results, not least due to the fact that not enough funds were allocated for many experiments. However, it cannot be denied that some forms of complementary medicine, namely acupuncture and meditation, are effective for conditions such as headache, neck pain and stress. And certainly do not doubt the popularity of alternative medicine. Such methods of treatment have long been widely used in Asian countries, and in Japan, 75% of residents regularly resort to their help. Now their popularity is growing in the West. Alternative medicine is becoming increasingly popular, although in many cases its effectiveness has not yet been proven by large-scale controlled clinical trials. Herbal medicines are a form of alternative medicine. Many patients trust them infinitely, and most doctors scold them. Once upon a time, doctors chose treatment for their patients based on personal beliefs, information they received many years ago in medical educational institutions or on the advice of their tennis partners. Sometimes this approach worked, sometimes it didn't. Evidence-based medicine is trying to put such decisions on a more scientific foundation based on the results of carefully controlled clinical trials. Now doctors can use databases via the internet, which contain the latest information on the most effective methods of treatment based on reviews of clinical trials conducted by experts with international recognition. But whether they actually do it is another question. Many doctors still prefer to act independently. Either they are too busy to read the reports, or they are suspicious of the reliability of clinical trials, or they do not want to limit themselves and thoughtlessly apply proven methods of treatment in quotes. However, enthusiasts of evidence-based medicine insist that doctors must always combine hard evidence with their judgments about the needs of the patient. Every doctor has their favorite medications and treatments, but where is the evidence that you are getting the best treatment? Imagine being given a pill and being told that it will eliminate the headache and your condition will improve, even though the pill contains nothing but chalk. This is a placebo effect, from Latin I will like it. In medicine, this term is used to describe treatments that have no real medical effect and work on the power of persuasion. First described in the 1920s, today the placebo effect is an integral part of evidence-based medicine. In clinical trials, drugs are compared with placebo. It can be a pill that looks exactly like a real medicine, but does not contain medications. Or acupuncture needles that look convincing and are just as convincing to the touch, but don't actually pierce the skin. In a random controlled trial, half of the patients receive real medications, and the other half receive a placebo. If both groups show the same improvement in the condition, it becomes clear that the new drug is useless. The placebo effect is incredibly strong and its effectiveness even increases if the patient receives a larger tablet, pink pills, they are white or if they are prescribed by a respected doctor. The pill does not necessarily have to contain medications. Thanks to the placebo effect, it seems to you that you feel better, although now you know that the effect may not be that much.